Okay. Get him up on the screen. Okay, so our final presenter today is Gheric from Georgia Tech. It's going to be sharing with us a spatially adaptive AR content.
Okay. There we go.
Awesome.
Okay. Hi, everyone. I'm Gheric Speiginer, working at the Augmented Environments Lab at Georgia Tech, where we've been doing research related to building AR toolkits for the past 15 years. And so the problem that we're trying to solve is how can designers build content that will look and behave reasonably, especially in the context of complex, dynamically changing environments. And our solution, we call it Spatially Adaptive AR. I like to think of this as being analogous to responsive web design. But instead of adapting content to screen size and resolution, we're adapting content to the dynamically changing complex spatial relationships in the 3D environment. So let me tell you more about that. So we know that AR systems depend on knowledge of the world, and you have a spectrum here where you have a small amount of knowledge or an unmodeled world and a completely modeled world. And depending on how much information you have, how modeled the world is, it depends on the kind of things you can do with AR. But all this world knowledge can be queried and used for design. So a designer may want to determine, let's say I have this piece of content and I want to know how much room does it take up on the screen right now in this very moment. And so the answer to all these questions, they're answers that are changing continuously and dynamically. And it may be feasible for a designer to, let's say, figure out how to compute the answer to one of these questions themselves. But it becomes infeasible when you start asking lots of questions, and then suddenly the designer has to know how to do all this complex 3D math, quaternions, 3D matrices. It can just become very intractable. So basically, as the knowledge of the world becomes more detailed, you need a way to reason about that knowledge and use it. And so there's two different approaches that we're thinking about in how you can leverage this knowledge. And one is the top-down approach, in which AR systems are able to leverage this world knowledge and present content more effectively. So this is kind of akin to like a window manager, where it's actually adjusting the content based on the current use case or the current settings. So, for example, let's say you have a lot of content and it's very cluttered, or it could be cluttered. You have overlapping augmentations. A top-down system would move these augmentations around to their more optimal presentation, so that they're not, for example, blocking somebody's face or overlapping each other. Bottom-up approach, in this case, is exposing these metrics, this world knowledge, to designers in a way that lets them adapt the content themselves so that it's presented more effectively. And ideally, of course, an AR application would benefit from a combination of both of these approaches. However, right now we're focusing on this bottom-up approach. And so we see the key to this bottom-up approach being to express this world knowledge in a way, these metrics, in a way that are easy for designers to understand and use. And so, for example, you could have couple different questions, and they may seem like simple questions, but going about answering these questions, again, can be very complex. Lots of mathematics involved. So something simple might be, is this magazine right side up? Or how big is this ad on the display that the user is looking at right now? And even though these questions can involve a lot of complex mathematics to answer, generally the answers can be expressed in a way that's very simple, in a way that can make sense for the designer. So in general, they could be simple values. It really depends on what the metric is. They could be some kind of vector rotation. But the idea is to somehow express these kind of queries, or the answers to these queries, in a way that can be usable for designers. And another way to think about how these different metrics can be organized is distance, orientation, movement, identity, and location. They're sort of like the primitives of world knowledge. So all of this we're doing in the context of Argon and Argon.js. Argon is a browser which provides JavaScript extensions for key enabling technologies. This is tracking and sensing. Right now, we're focusing, right now we're just doing Vuforia, but we do plan on extending this to other kinds of trackers as well, other kinds of sensing systems. And the Argon browser has a UI that's specifically designed for AR-capable apps. And then we also have Argon.js, which is a cross-platform API toolkit for developing AR-capable web apps. And so the idea behind Argon.js is that eventually the Argon browser will no longer be needed once the augmented web supports all the kinds of technologies that you'd want, native tracking, Vuforia-like tracking, high-performance tracking, and all that. Then the Argon browser will be obsolete, and Argon.js will allow people to build apps that work on different browsers. And this includes wearables, head mounts, tablets, phones, etc. And so the Ethereal.js toolkit we're building on top of Argon, and this goes back to the spatial adaptivity. So in the Ethereal.js toolkit, we're basically providing extensions to the 3.js, which is this toolkit for building basically 3D content on the web. And we're basically just extending the 3.js objects in order to allow designers to access these kinds of metrics anywhere in their code, and providing different structures for them to handle adapting to those metrics as they're changing. So a couple examples of some of the different kinds of adaptation effects that are possible with Ethereal, without going into detail on exactly how this works. The top one there is really kind of just adapting to distance from the user. So when the content is far away, the size of that content is shifting such that the text, for example, is still the same size no matter how far you are. The bottom one is adapting to the angle between the user and the content. So early prototype combining these multiple adaptation effects. This isn't necessarily the right way to do things. Still sort of in the early experimentation phase, so we were just playing around with different things. But you can see here, even when we back up, move further away, you can see that you see less content on the screen. You'll see just in a moment. You kind of see a simpler view of that augmentation there, whereas when you come in closer you see more details, and the titles, for example, are adapting dynamically in order to try to maintain a constant size on the screen. So this is a more recent example of spatial adaptivity in AR. We're doing a lot of the same things here, adapting to distance, adapting to distance from the center of the screen, adapting to angle, all these different things that you see here, these animations, parallax effect, they're all basically encoded as adaptations to dynamic adaptations to these spatial relationships. And all of this here that you're looking at is done using standard web technologies, so JavaScript, HTML, CSS. This actually isn't even WebGL, it's just divs in 3D. And so we're using GreenSap animation platform here to do the different tweening, Vuforia for the tracking. And this is all running in the Argon browser, running off a standard HTTP server. So it's just an HTML file posted anywhere by anyone. And so in summary, the Ethereal.js approach, as far as spatial adaptivity concerns, this is the bottom-up approach we're using right now, is spatial design metrics and spatial control flow. Eventually, we would like to start looking into more of this top-down adaptivity as well, being able to combine both together. But this is what we're doing right now. And do you guys have any questions?
Any questions? Okay, I have tons for you, but I will take those offline because lunch follows this. So, so thanks a lot to the presenters. Definitely a big round of applause. Those that are supporting